All right, so let's take a look at this example problem here. So it tells us that federal regulations set an upper limit of 50 parts per million of ammonia in the air in a work environment. Okay, and so they say 50 molecules of NH3 for every million molecules in the air. And it's talking about the air from this manufacturing operation is drawn through a solution that contains a certain amount of hydrochloric acid, and then they react according to this reaction 1-to-1 mole ratio. And then it tells us what they did. So they draw air through the acid solution for 10 minutes. You would assume that the ammonia in the air would react with the hydrochloric acid. Then they titrate the acid. They tell you how much base it took to titrate the acid. And then they want you to tell how many grams of NH3 were brought through the solution. And then they want you to tell the ppm of that. And then they want you to tell whether or not the manufacturer is actually in compliance with the regulation. Now, this is a pretty lengthy and complicated problem, but is this a real is this a real world possible application that yeah. This is one method. Now, if I was the compliance officer with the OSHA or whatever agency would be checking this, I would want to have an ammonia meter that I just hold up in the air that tells me, what the ppm of ammonia is. But if you didn't, this is one way that you could do it with very basic equipment. So, based on what they've given us here, could we figure out how much acid was left in the solution? Because they told us how much ammonia it took to neutralize the remaining acid. So we can figure out how much. So this is my planning phase. I'm going to figure out how much hydrochloric acid is left in the solution after the ammonia passes through. Then I'm going to subtract that from the amount of hydrochloric acid that was present to begin with. The difference between those two things will give me the amount of hydrochloric acid that actually reacted with ammonia. From that, I'll calculate how many moles of ammonia and then how many grams of ammonia were actually drawn through the solution. So that's going to be the approach that I take to go through and solve part A anyways. So let's do that. So the 13.1 milliliters of sodium hydroxide. Oh my. Let's go ahead and change this into liters. I'm going to move the decimal place over and nix that. And then this is saying 0.0588 molar. So that means there's 0.0588 moles of sodium hydroxide in one liter. Right. So let's take in moles per liter. So in 1 liter of sodium hydroxide solution. So liters of sodium hydroxide cancels out. And then the equation says that for every 1 mole of sodium hydroxide, there's 1 mole of HCl. All right, so time to find a calculator and do some calculating. All right, so here's what I got that's going to be moles of HCl. So that was the moles of HCl remaining in the solution after they bubbled the ammonia through it for a while. So I'm not rounding off yet because I'm not going to do significant figures until I get to the bitter end of this problem. Now, let's take that and compare it to the original amount that was present in that solution. So we started off, by the way, I could use the molarity equation here, but I'm going to do this as a conversion factor because I can mainly. Oh my goodness, that's in milliliters as well. So it's like 100 milliliters. And I'm going to go ahead and change it to liters. So that's going to make it move it the decimal 3 places. So instead of a 2, that's going to be like a -1 there. And then I'll do the same thing. So they told us it was 0.0105 molar HCl. All right, and then you'll do, let's see, 0.1. So that's going to be 0.00105 moles of HCl. Yeah.
Oh, yeah.
Yeah. Okay. All right. Yeah, and the liters of HCl canceled out. So there you go. Now, what should I do with these to figure out how much HCl reacted with the ammonia? Subtract. So I'm just going to write a little note of what I did there. I'm not going to copy all those numbers again because I really just don't want to. All right, and when I subtracted them, I got, dear goodness, 0.000279772. You might confirm that. Yeah, okay. And that's going to be moles of HCl. And I really wish I'd written it on the other side of the page because I need to do dimensional analysis with, well, that's not that bad. Okay, so let's take this over here. It would be the same. Okay, so there's a 1-to-1 ratio. I'm going to justify that just by writing this out. So 1 mole of HCl reacts with 1 mole of NH3. And then they asked me for the grams of NH3. So that's what I'm going to do now is convert. Do what now? Yeah. Did I hear molar mass? Is that what was said back there? Yeah. So we're going to molar mass this thing and go to 17 grams. So previous answer times 17. Easy enough to do in your calculator, but once you've written it out, you have the justification, and if you do get lost somewhere in the problem, that'll help you figure out where you're at. So once I did that, I got 0.004. Let's say about 3 significant figures would be appropriate there. So 476. Let's pause. Did anybody notice that the definition they gave us of ppm here was different than the definition of ppm in the notes? Because ppm in the notes is grams of, whatever thing you're interested in divided by total grams times a million. Yeah. And this one is saying they want you to do molecules of this per million molecules in the air. Yeah. So, and that's an interesting difference, I guess, because it is actually done both ways, and that's utterly confusing for somebody that comes in and they're trying to figure out, am I doing this ppm by mass or ppm by molecules? And since this one specifies it wants per molecule, then we're going to have to do a little bit more thinking on this one to get there. So basically, we need to figure out how many. Wait, what are we doing? Yeah, how many ppm are in the air? Okay, so basically, we need to figure out how many molecules of NH3 and then how many molecules of air and divide the two by each other, and we should come out to what they are counting as the correct answer. So let's take that on and see where we can go from there. All right, I got this number. So it's a 1-to-1 ratio. So I'm like, yeah, the moles of NH3 are the same as the moles of HCl. And I'm going to go to molecules of NH3. Do y'all even remember how to do that? I know it's been a while. Yeah, Avogadro's number 6.02 E23 molecules per 1 mole. All right, so let's math that out. All right, and I got 1.68 391 something, yeah. E20. It's a lot of molecules, right? Okay, and let's see. They told us that the challenging part of this is going to be figuring out how many molecules of air went through this thing. So, yeah. Thinking about it. So we drew air through at a rate of 10 liters per minute for 10 minutes. So how many liters of air did we? About 100 liters of air. Let's see where we can go with the information that they gave us there. Oh, goody. They did give us useful things. That's nice. Okay, 1.2 grams per liter. And then they told us the average molar mass was 29 grams per mole. All right, and then for moles, where do we really need to get? Molecules of air. So let's go to molecules now. 6.02 E23 per mole. So liters cancels, grams cancels, moles cancels, and we're at molecules of air. All right, so let's math in the calculator. Yes. I may have to move it around a little bit more, but that's, yeah. Can you see that better? Yeah, good deal. All right. Oh, snap. I forgot where I was at. Okay. 6.02, 23. And then divide by 29. All right. Did y'all get that or no? Did I do something wrong? Okay. All right, so we're going to take these two, and to do parts per million, you're going to divide them and then multiply them by a million. All right, so when you do that, I came out with like 67.6. All right, and then are we in compliance with the regulations? It said 50 parts per million. We're at 67.6, so the answer is no. We're too high. Yep. Too much ammonia in the air. Yeah.